relative to the orientation of our block now. Okay. And I'm going to make you more confused. Not confused, aware. Okay, not confused. Apologize. So the axis I've drawn, this is your shear XY. And this direction over here, right? This is your Y direction. So these are your extremes, your edges. So one is positive C, the other one is negative C, right? So positive C is negative C does not really matter because over here in the end you squared them, so does not really matter. So if we were to sketch this, we are aware that when Y is equal to 0, what we have over here, we have your tau max is equal to 3 Vy over 2A, right? And then if you sketch the shear XY expression out as a function of Y, you get a curve looking like this. Okay, so all I need to do now is I copy, and it's set face, it's not smiling face. Okay, I paste and then I flip it around, and there you go. Okay, close enough. Okay, right. So this is the shear stress distribution profile. Okay, this is our shear stress distribution profile. Now I'm going to introduce you to another equation where stress X is equal to my over I, right? Now, does that look familiar to you guys? Yes or no? Right? It looks awfully familiar, and this is because of this is induced by what? Bending what? Moment. All right, this is induced by bending moment. So you have another. I'm going to draw. So this. So we are going to assume that the structure is under a vertical force. It will induce a shear force and a what? A bending moment, right? So over here, you have normal stress in the X direction, right? So we are going to have a Y. Same thing like before, right? So the problem is this. What can you all tell me about the shear force and the bending moment stresses? What can you tell me? Anyone? So this is my C. Yes, I hear a mic that has been unmuted. What can you
one
see?
One seems to be like the derivative of the other. Like one is linear and the other one is quadratic. Like the shear.
Okay. Too much math. Think simple. Observe the graph. Think simple for me. Come on. What can you observe? So I will give you a hint. So we realize that over here, right?
Oh, one you get negative and the other one you get positive?
No, you're close. What do you realize? At the neutral axis, right? Stress X is equal to what? 0. Yes or no? Right? Over here, right? At the neutral axis, the shear stress is what? It's actually maximum. Am I right? So over here you have in 0. Over here you have it as is what? As its maximum. So when you design your structure, what will you use? One is at a maximum shear, 0 normal stress, and the other one you have 0 shear, maximum normal stress, right? Right, what will you use now? Okay, but don't worry about that. That is about maybe 4 weeks later where we integrate normal stress and shear stress together. Okay, but now is how to, so all of you by now, are able to calculate normal stress already, induced by axial loading, induced by bending moment in two different axes, and centric and eccentric loading. Now we're going to introduce what? Shear force induced by two different directions. Okay, so I'm building up your competency to analyze the structure that we have in our introduction. Okay, right. So we are going to go into our first example now. Okay, we're going to go. So we're going to look into this example now. So you can get this example from your avenue to learn. Okay, we're going to go into this example. Right. And I'm going to do more for this example than what is requested. Okay, example number 1. So what we see over here is we have a beam and loading shown. Okay, so we want to determine the shearing stress at point A and the shearing stress at point B. Okay, so we're going to go further than that, and I'll tell you what is this further that we're going to do. Okay, so I will write down the sequence of a solution. Okay, what steps are we going to take? So first thing we're going to do is we're going to draw our free body diagram. Okay, and then after that we are going to calculate the reaction at point A and point B. And then I'm aware that you guys have done this, maybe a very quick recap. We're going to quickly sketch the shear force. And bending moment diagram. Then from here, we are going to look into the shearing stress. And again, in the shearing stress, we need to identify our centroid. We have to find our first moment of area. As a variable, as a function of y. Now this is the extra bit, okay? And I want us to derive the shearing stress distribution equation. And then finally, we're going to find what is the shear at point A and what is the shear at point B. So over here, this is extra. Okay, I want you to go into detail of finding first moment of area as a function of y. Nothing you cannot handle. I'll repeat again, nothing you cannot handle, okay? So the only region that I'll go quickly is the centroid. Okay, the centroid I will pass very quickly, and also the second moment of area I'll pass. So sorry, so we still also I missed something. Okay, so from the centroid we have to find our second moment of area. Okay, so these two I will not do it in detail. I will just show you the numbers and we go from there. Right. So we're going to firstly construct our free body diagram. Okay. So very quickly, so you guys are really expert free. Before we go into our free body diagram, based on this figure, we're going to call this our X and our Y, and then this over here is our rotation about Z. On the next diagram is a cross section view, and this is our Y, and this is our Z, and this is our rotation about X. Okay, we get that clear first. So we're going to draw our free body diagram. So we're going to construct free body diagram, right? So you write out your transformation, X and Y, rotation about Z, and you sketch out your beam. So this is our beam. So this is our AY, and this is our BY. And then we have a load coming down, and this load coming down is at 180 times 10 to the power 3 Newton. Okay, and then we have a fixed set of geometries. This is equal to 0.5 meters, and the other one is equal to 0.5 meters. So when that's the case, we can go for positive static analysis. Summation of forces in the y direction will be equal to 0. Then you have AY plus by BY minus by 180 times 10 to the power 3. The whole thing is equal to 0. So this will be your equation number 1. Okay, so from here we know that based on symmetrical loading, okay, based on symmetrical loading and geometry about the y-axis, right? So we can state that AY is equal to BY, okay? And then we can substitute into our equation number 1. Okay, we can do that substitution. So we now know when you substitute that, you get 2AY is equal to 180 times 10 to the power 3. And then we know that AY from here is equal to 90 times 10 to the power 3 Newton. Okay. So from here, we are going to quickly sketch our, okay, I'm going to use the next page. Give me a short moment, okay? I'm going to close my windows. You all can hear a disruption, right? Background noise. My neighbors is doing his lawn. Sorry about this. Right. Thank you for waiting. So from here, we can construct our shear force diagram. Okay, so we're going to draw our shear force diagram. So this is X. This is V. And V is in kilonewton. And then we have 90 over here. Then we have minus 90. And then we have 0.5. And then we have 1. Over here is in meters. So how our shear force diagram, it will look like this, okay? So it will start from the top, 90 until 0.5. And 0.5 over there. It will come down, okay, by 180, right? Because at the center point, you have 180 coming down, right? Then you run for minus 90, and then at point B, you'll go up by 90. Okay, so that is your shear force diagram, right? So from here, what we discover is that Vmax is equal to 90 times 10 to the power 3 Newton. Okay, so we are looking at the magnitude for this case. Okay, so we know that our Vmax is equal to 90 times 10 to the power 3, right? So quickly, shear force diagram, bending moment diagram very quickly. So bending moment diagram. So you have X in meters again. And I'm going to focus on just the positive side of the bending moment equation or bending moment diagram. Why positive? Any idea? Can anyone tell me why are we focusing on the positive of the bending moment diagram? Anyone? Can you remember?